So you'd send your job out to the cloud. The computation would occur in some server farm remotely, and then the output would be sent back to you. I think that would be the modality for quantum computing as well. In which case, you don't necessarily need to have a portable quantum computer, but you do need to have quantum communication from your device to that remote quantum computer.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And before we get started, just wanted to mention that we have released material science merchandise for those of you who want to support us or just express your passion for MSE. You can check out more of the designs at itsmaterialworldpodcast.com/shop or by clicking the link in the description. All right, let's get right into it. Special thanks to MatMatch for sponsoring this episode. Hello, everyone. We are so excited to talk to today's guest, Professor Mark Hersam. Dr. Hersam is a material science and engineering professor at Northwestern University. And with his research group, he has authored over 500 peer-reviewed publications regarding nanoscale materials for applications in information technology, biotech, nanotechnology, and alternative energy. He is a recipient of the MacArthur Genius Award and has made major breakthroughs in nanotechnology. That was an article from the National Science Foundation. So in today's episode, we'll cover the properties of carbon nanotubes and dive into its many applications. So thank you so much, Mark, for joining us today.
Yeah, my pleasure. Thank you for having me.
Yeah, thanks, Mark. So I guess just to start us off real quick, what is a carbon nanotube? And can you describe some of the properties that make them so unique?
Sure. Yeah, so when I talk about a carbon nanotube, I like to start with graphene. So I should introduce graphene first. And the way to think about graphene is to start with graphite. So graphite is basically the lead in your pencils. And as you know, when you drag a pencil across a sheet of paper, the pencil lead rubs off. And the reason this is true is that graphite has weak bonding between its layers, and therefore it's easy to peel it away or exfoliate it. And if you peel it all the way down to the single atom thickness limit, you'd have a sheet of graphene. If you then imagine taking that sheet of graphene and rolling it up into a cylinder, that would be the structure of a carbon nanotube. And the typical diameter of a carbon nanotube is about 1 nanometer, and the length can be hundreds of nanometers to up to centimeters in length. So the aspect ratio, the ratio of the length to the diameter, is thousands to millions. So this is a one-dimensional form of carbon. It's sort of like a wire, and its properties are quite diverse, depending upon the details of its structure. In particular, its diameter and the degree of twist in the graphene sheet as you roll up that cylinder. Some of the nanotubes are metallic in nature and may be good as a conductive element in an integrated circuit. Other nanotubes are semiconducting, which would replace the active region of a transistor, for example. In terms of other properties, carbon nanotubes are also good emitters and absorbers of light, particularly in the near infrared, which is the wavelength of fiber optic communication and biomedical imaging. Also, they're very mechanically resilient, so you can use them in flexible electronic devices.
Awesome. That was a huge range of applications. So how can just graphene rolled up have so many different applications in such different fields?
Yeah, so I think the key reason is that if you imagine taking a sheet, like a sheet of paper, and rolling it up into a cylinder, you do have two free parameters, the diameter and then the twist. And it turns out that implies that there's hundreds of different distinct carbon nanotube structures. And each of those structures will have a different set of properties. And consequently, if you could isolate the different structures of carbon nanotubes, you could go after a wide range of applications.
Wait, so let's then maybe just talk about one of the specific applications. So with nanoelectronics, what aspect of maybe its chirality or its diameter, what combination gives its electronic properties?
Yeah, so it turns out among these hundreds of possible chiralities, 2/3 of them are semiconducting.
Mhm.
And so those are the ones you'd want to use for the active element in your integrated circuit, like the transistor. And then among those semiconducting nanotubes, the band gap varies as a function of the diameter, and that the band gap will determine properties such as what wavelength of light is absorbed by the carbon nanotube. It will also dictate how well you can make electrical contact to the carbon nanotube. And so the larger diameter tubes tend to be a little bit better for making low resistance contacts, and therefore you can pass more current through them.
Gotcha.
So that's the range you typically work in for electronic applications.
Okay, so then, since we're talking about materials at the nanoscale, I've always heard that, especially with carbon nanotubes, the processing can lead to a lot of challenges when you're scaling up. So how are carbon nanotubes made, and is that process scalable to like a commercial level?
Right. Yeah. So the way carbon nanotubes are synthesized is you need to have a catalyst particle, and the catalyst is typically a metal. Common examples would be iron or cobalt or nickel or molybdenum. Then you need to have a carbon source, which is typically a gas, carbon-containing gas, which could be something like methane or carbon monoxide. And then you need to have high temperature. And high temperature could be in the form of a furnace or a laser or a plasma. And if you get the conditions right, then carbon nanotubes will grow. And this process is one which has been scaled up. So you can produce large quantities of carbon nanotubes. The real challenge, though, is that the exact structure that you get is not well controlled. And so you get a range of these different carbon nanotube structures. And as we talked about before, each nanotube structure is a different set of properties. And so the bigger challenge is how do you separate them from one another after you've grown a large quantity of them?
I feel like that had to do with your research a little bit, and I know you've told us this before, but maybe you can dive into that briefly.
Absolutely. Yeah, so this was the challenge in the field in the early days. How can you take this mixture of carbon nanotubes that is produced during the synthesis and then separate them with atomic precision in a scalable manner? And our lab took on that challenge. And the way we looked at the problem is that if you remember the dimensions of a nanotube, it's about a nanometer in diameter and can be much longer in length. That's very similar to the size of a biological macromolecule like DNA. And consequently, since biochemists for decades have been figuring out how to do exquisite biochemical separations, it stood to reason that those methods could be adapted to the carbon nanotube separation problem. And that's exactly what we did. One of those methods is called density gradient ultracentrifugation, or DGU. And in this process, what you do is you separate, normally in biochemistry, your biological macromolecules by their buoyant density. This we adapted to carbon nanotubes. And it turns out that the buoyant density of a carbon nanotube depends upon its structure. And as a result, the density gradient process achieves separation of carbon nanotube structure. Another piece of the story is that because this was born out of biochemistry, the pharmaceutical industry had already figured out how to scale up this process. And so we could borrow those strategies and adapt them to the carbon nanotube separation problem. And so once we did this in our university research lab, we were able to found a company called Nanointegris that very rapidly scaled up this process to the industrial scale.
Yeah, that's a great story. And I kind of like the crossover between carbon nanotubes and stuff we already know about with DNA. But I guess a question I have is, when you create the nanotubes themselves, can you get like a tight grouping, or is it kind of you get what you get with a whole wide range of diameter and chirality?
Yeah, so you're right. I mean, you may think, why not just grow the chirality you want from the beginning? Then you can skip the separation. And that is a widely explored strategy. And some progress has been made. So you can get a much narrower range of diameters and structures nowadays than you could a decade ago or 2 decades ago. But nevertheless, even the best synthetic strategies today don't have perfect control. And so the way we look at it is anything that can be done on the synthesis side to narrow the range is good for us, because then our yield is higher after the separation process. So we're the biggest cheerleaders out there for improving the synthesis. But until someone does it perfectly, and I have my doubts that will ever be achievable, there'll still be a need for separation to take it the final few steps to sufficiently homogeneous samples for applications.
Yeah, I'm sure, especially with the trade-off, I bet like potentially it could be done, but who knows how many like times more expensive it could be. But I guess going off that, so what happens to the carbon nanotubes that you do make and separate out that might not be potentially for your application? Are there enough applications to where all of it's used, or will you always have some waste?
Yeah, so another detail which is relevant is when you try to grow carbon nanotubes, sometimes you get other forms of carbon in addition, including you may get some graphene that we talked about before, you may get some other graphitic carbon that's ill-defined. Basically, the output of the synthesis looks like soot. And you need to, of course, remove everything that's not a carbon nanotube first, and then among the carbon nanotubes, separate them by their structure. And so that other carbonaceous material will have lower value applications. It still might be useful. That could be used in applications like tires. You know, tires have a lot of poorly defined carbon in it. That gives you the black color of tires. So that material may be used in those I would call lower tech applications, but the really refined carbon nanotubes you're going to want to use in a high value application. And that will often be in electronics, but can also be in other applications, including in the energy space.
Gotcha. So they are being used at like the industrial scale. It's not just purely at the research level. So it is being like very much commercialized, especially when it comes to the electronics industry.
Yeah, so the electronics industry is definitely looking at these materials, and they've basically shown, in particular, IBM showed that these semiconducting carbon nanotubes can outperform the incumbent semiconductor, namely silicon, when you get down to the very short channel limit. And that is, of course, where the field is going. The whole business model of the semiconductor industry is to make the size of the transistor smaller. And when you get to these very short channel length limit, then the nanotubes can outperform silicon. So that would be the highest performance application that could be used. But as we talked about before, while 2/3 of the nanotubes are semiconducting, that means 1/3 are metallic. And the metallic nanotubes can be used in applications where you just need conductivity. And a good example of that would be in batteries. So in batteries, you have the active material, which is, for example, in a lithium-ion battery, storing or discharging lithium. But in those electrodes, you still need to have conductive additives to connect together all of the active materials, and that could be an application for the metallic carbon nanotubes.
Yeah, I do battery research in my lab, and I do a lot of slurries, and that's like one of the biggest problems is that sometimes you're not activating the entire active mass, and it's all about how you can connect the conductivity of it. But beyond that is how expensive are carbon nanotubes compared to like silicon or more traditional materials?
Yeah, so that's a very, very good question. And it depends what what grade of nanotube you want and how much purity is required for an application. But if we talk about the highest grade material, for example, you went to Nanotech's website and you looked at their highest grade material, you would find that it's on the order of, say, hundreds to hundreds of dollars per milligram.
Oh, wow.
Wow.
Which means that it's like $100,000 per gram. And if you compare that to, say, gold is typically like $50 to $60 per gram. So this sounds really expensive.
Oh my goodness.
The thing that you should think about though is for electronics, all you need is a thin coating of carbon nanotubes on the top surface of your wafer.
Mm-hmm.
And so a question that maybe I could ask you is, what mass of nanotubes do you think is needed to coat a 12-inch wafer, which would be what Intel would use to make 100 microprocessors?
Okay. I was going to say a gram at first, but now that you told me it's $100,000, there's no way it's a gram.
That's like the highest grade. Okay.
I'm thinking more like 0.1 milligrams now that I'm hearing these prices. I don't know. What do you think?
So I was just trying to do the math of like how many carbon nanotubes would be needed to like cover a square foot. And like, okay, so a carbon nanotube is, you mentioned the aspect ratio. So like the diameter is like in the nanometer scale. So that's like 10 to the negative 9th meters. But then like the length could be even in the centimeter range. So I got really confused with the math, but now when I'm trying to like think of the pricing, like I was thinking it was like on the scale of like millions of carbon nanotubes to fit that 12-inch by 12-inch, but then that could be a ton, like that's a ton of money. So I don't know.
I'm gonna go with 0.1 milligrams. That's my guess.
And David is correct.
Oh my goodness!
It's about 0.1 milligrams. So now,
wow.
now we're talking about something like $10 per wafer.
Mm-hmm.
And if each wafer is making 100 microprocessors, the math makes sense. I mean, the economics make sense. And so that's the key point, is the highest grade nanotubes are going to be used in thin film applications. And when you go to the thin film limit, since they're only nanometer in diameter, it only requires, say, 1/10 of a milligram to coat a 12-inch wafer. And now things make sense, and you can imagine it becoming profitable. But if you want to make a bulk material, like you wanted to build a bridge out of carbon nanotubes, that's probably not going to work economically.
Yeah. And I guess I'm really interested, if it's $100,000 now for a gram, before you scaled it up, what would a gram cost, do you know?
Well, the cost is interestingly completely embedded in the raw material.
Oh, okay.
So the raw material is expensive from the beginning. So the separation is sort of an incremental cost on top of that, which means that any advances in synthesis, which give you a higher yield of the nanotubes versus the unwanted soot, immediately translates into a lower cost of the purified material. So that's I think an important thing to note.
Mm-hmm.
Wow. You nailed it, David. I am so proud of you.
I can't believe it.
It was like purely, you thought about it the right way, where it's like pricing what makes sense. I was trying to do all this weird math. It didn't work. But we can dive into that application even further. So, in previous conversations, one of the applications we talked about was like carbon nanotubes in solar cells, as well as like optical fiber. So what properties specifically let carbon nanotubes excel in those applications?
Yeah. So there's a different answer for each of those cases. So maybe we can start with, say, fiber optics.
Sure.
And fiber optics, the sweet spot is the near infrared. And in the near infrared, there's not a lot of material options, but carbon nanotubes are one of them. And the typical diameters of carbon nanotubes imply that they absorb light very effectively in the near infrared. So the semiconducting carbon nanotubes we used in that case. In the case of the solar cell, the property of nanotubes that's useful is that the metallic nanotubes don't absorb a lot of light at visible wavelengths. And as a result, you can use the nanotubes as the electrical contacts in a solar cell, because the solar cell, you need to get the light into the solar cell, convert it to electricity, and then get the electricity out, which means you need to have at least one of the contacts being optically transparent but electrically conductive.
Mm-hmm.
And carbon nanotubes have that relatively unusual combination of properties. If you think about other conductive materials like copper, they're obviously not transparent. You can't see through them.
Mm-hmm.
So nanotubes are relatively unique in that regard.
And so when we talk about fiber optics, the general premise of fiber optics is we have two light sources and one shoots through a glass tube and it reflects back and forth until it reaches the other sensor. Would the carbon nanotubes be used in those sensors to detect more like differentiating light patterns to transmit more information? Or what's the use in fiber optics?
Yeah, so you're right. For fiber optic, you need to have an emitter
Mm-hmm.
of the near infrared light and then a detector at the other end of the fiber. And the nanotubes can do either. They're so-called direct bandgap semiconductors, which means that you can put current into them and get light out. Or if you have light coming in, you can get current out. And so you can run the device in reverse to get the opposite property. And that makes them useful at both ends of the fiber optic cable.
Wow. And so you mentioned the infrared related properties with carbon nanotubes as well for the fiber optics. Is that the same property that makes it useful in biomedical imaging?
Right, yeah. So in biomedical imaging, near infrared is also useful because biological tissue is relatively transparent at near infrared wavelengths. And so if you want to do subsurface imaging with light, obviously we can't use visible light because our skin is not transparent at visible wavelengths, but at near infrared, it's relatively transparent. And so you need to have imaging contrast agents that are sensitive at those wavelengths. So nanotubes would be a candidate in that regard.
Wow. So you would eat some nanotubes and then that would be the contrast for the image?
So carbon nanotubes could be used in vivo in that context. Now you have to be careful about toxicity right? and issues like that. And we've worked a lot with medical school at Northwestern and also at UCLA on this topic. And it turns out that nanotubes can be made biocompatible if you keep them individualized. So one thing we didn't talk about yet is that if you imagine these very small fibers, they can also begin to aggregate into larger bundles. And if you keep them from bundling or aggregating, then they can be cleared from the body using the natural mechanism of the body. It's when they start to aggregate that you can get a sort of accumulation and some toxic responses. So a key innovation is coming up with coatings on the nanotubes to keep them from aggregating in an in vivo setting.
Interesting. Is that similar to, so I've heard this term with gold nanoparticles, but when you use gold in the body, you functionalize it, like you combine it with ligands. Is that similar to this at all in terms of like making it more biocompatible, or is that totally different?
It's similar in the sense that you need to have a coating on the nanotubes. Mm-hmm. There's some subtle differences in that the properties of the nanotubes really rely upon the bonding in the carbon network to be preserved. And when you functionalize, as you called it, there's two ways of doing it. One is to attach with a strong covalent bond, which is how you would likely do it with gold. The problem with doing that with a carbon nanotube is that now you've disrupted the bonding of the nanotube, which would disrupt its properties. So you need to instead use a non-covalent functionalization, which relies upon other forms of bonding, like hydrogen bonding or van der Waals bonding. That has been worked out for nanotubes and has facilitated its use in a biomedical setting.
Man, those are two super cool applications. And moving on to another application we talked about, and we've talked about this slightly briefly earlier, was energy storage. So we talked about how it could be used to kind of connect different groups of active material in batteries. How else can they be used, or maybe more generally in an actual battery system, could they use to be improve the performance?
Yeah, so in a normal battery, the conductive additive is typically carbon black. Carbon black is, again, what's used in tires. It's a pretty low grade form of carbon, which has the advantage that it's cheap, but that also implies that the properties are not that great. And as a result, carbon nanotubes can add value in that context. The other thing that I'll say is, in a battery electrode, it's made up of a bunch of relatively small particles. Those are the active materials that are storing the lithium. And if you want to connect together a bunch of particles, the best way to do it is to use a long yarn-like structure, because you can connect multiple particles together with one of those. So a carbon nanotube, of course, has that sort of one-dimensional structure to it, which facilitates the transport throughout the network of particles in the battery. Also, because they're fiber-like, they act as a mechanical reinforcement to the electrode. And one challenge in batteries is making the electrodes thick while maintaining their mechanical integrity. And if you add in some carbon nanotubes, they also provide the mechanical reinforcement in the battery. So you get a double advantage there in terms of the electrical conductivity and the mechanical integrity of the battery electrode.
And with the theory behind why you want a thicker electrode is just you would have a higher energy density?
Correct. So generally speaking, you want to pack in as much active material as possible. Because if you had a thin active layer, then you're going to need to have more layers in the battery overall, and therefore more current collectors for each layer, and the current collectors are just dead weight in the battery. So the thicker the active material per current collector layer, the better. So you want to go as thick as possible. And one thing that limits you in terms of thickness is mechanical integrity, and the other is electrical conductivity. And the nanotube addresses both of those issues.
Cool. And so you mentioned the yarn-like structure of carbon nanotubes is appealing. So I know the range of the lengths is very large. So in these applications, what is that general range for the length of the carbon nanotubes?
Yeah, so I would say probably you'd find that to be on the order of microns, maybe tens of microns. And the reason is that the thickness of the electrodes tend to max out around tens of microns as well.
Oh, okay.
So that's sort of a natural fit for the battery application.
Gotcha. Cool. So I guess moving on to another related application, you mentioned semiconducting carbon nanotubes a lot, how that's 2/3 of them. And that can be used in inkjet printing for electronics, which can really affect the costs in sensors and IoT or Internet of Things applications. So there's a lot to unpack there. So maybe we can start with printing electronics and how that can lower costs in IoT applications, and then we can maybe get into the role of carbon nanotubes.
Yeah. So Yeah, as you mentioned, Internet of Things is sort of an emerging concept. It relies upon massively deployed sensors. Basically, if you have sensors everywhere, then you can monitor everything, and as a result, have an Internet of Things. For that to work, the sensors better be cheap. If we're going to tag every single item in the world, it's going to get expensive pretty quickly if each sensor is not inexpensive. And so if you did that with conventional processing, as is used for microelectronics, you would need to have $1 billion clean room in order to make those high performance sensors. So the manufacturing costs are a big limiting factor. Whereas if you think about technology where we pattern things at a large enough scale and cheap enough that we can just throw it away every day, you come to the idea of a printing press, because obviously, at least when people read newspapers, they were printed every day and delivered to everyone's doorstep, and you'd read it and you'd throw it out because it was so cheap to print. So printing is definitely a cheaper way of making something or patterning something than a $1 billion clean room. But that would require you to have an ink that's electronically functional, not just a dye to dye your newspaper so you can read it. And that's where we need to think about how we can get good electronic materials in solution. And as I alluded to before, the separation process we're using, this density gradient process, is actually done in solution, just like biochemistry is done in solution. So now we have the nanotubes already in solution. And if we adjust the viscosity of that solution to make it compatible with a printer, like an inkjet printer, now I can print the carbon nanotubes themselves, and they are electronically functional. And as a result, we can make the circuitry that goes inside of a sensor much less expensive than conventional processing.
And so when we talk about printing it onto like a silicon wafer or something, would it ever be able to replicate what we could do in a clean room, or is it more for that cheaper functional group of products?
That's right. Yeah. So when you're printing, there's some limitations compared to a clean room. So there's a reason that Intel stays in business with $1 billion clean room, because the performance is very high, and therefore they can charge a lot for their microprocessors. And as we also briefly mentioned before, the highest performance devices are very small. And what a printer cannot do is achieve the resolution that you would get in a clean room. So that's what you're trading off. You're going to much larger devices and therefore lower performance devices, but at a much cheaper cost. But for a lot of sensors, you don't need to have 1 billion transistors to detect the temperature or the humidity or some target analyte. You maybe only need a handful of transistors. So it doesn't matter if they're that big. And that's why you can still win in the sensing arena using a printed device.
So where are we at right now with inkjet printing for electronics? Like, what are the main challenges that are coming up in that application?
Yeah, so I think it's really an integration challenge, because you need to not only have the semiconducting component of the device, you still need to have electrical contacts. You still need to have so-called dielectric layers, which are the insulators that isolate one device from another. And while there are good inks for each of those, integrating them all together into a functioning system presents challenges. There may be interfacial issues or other incompatibilities between each material. So I think that's one of the key challenges. A lot of progress has been made and is being made, and some of the simplest devices, I think they're ready to go. But that would be the sort of the frontier problem, is to get to increasing complexity, which is basically a materials integration problem.
And so when we talk about putting nanotubes, because they perform better than silicon at nanometer resolution, is it having the same problem where we're having problem integrating it because it's a whole different material than silicon, or is it kind of just a one-for-one swap?
Yeah, so there definitely in the early days, materials integration was a big problem. And when you make a transistor really small, that means the semiconducting part is small, and therefore the contacts, electrical contacts, matter more than if you had a bigger device. And the electrical contacts in nanotubes were a problem for many years. That was eventually solved. And so I think that issue is pretty well in hand, but there's a manufacturing challenge in that for the highest performance devices, the nanotubes need to go down in an aligned manner. And if the nanotubes are in solution where they're randomly oriented, to get them to go down perfectly aligned with perfect spacing is a manufacturing challenge. So I'd say that's the frontier problem for the highest performance applications is how do you put the nanotubes where you want in a deterministic way that's scalable and inexpensive.
That seems like a pretty big challenge. Like it seemed like the whole separation thing took a while, and that's just separating by like, diameter and potentially like chirality. So I don't even know how you would align each and every carbon nanotube just how you want it.
Yeah, so a lot of people work on this, and there are some pretty interesting strategies that I think will likely be refined and ultimately be the answer. Mm-hmm. But if you imagine having logs in a river, which is sort of a macroscopic version of nanotubes in a solution.
Yeah.
One way to align them is with flow. So as the river flows more quickly, the logs are more likely to align with the flow direction than perpendicular to the flow direction. And so the control of flow would be a strategy for aligning nanotubes. And so that's basically true. And you can get nanotubes to be pretty well aligned by controlling the flow of the solution. The bigger challenge, though, is if the nanotubes get too close to one another, then they start to bundle. We talked a little bit about bundling before, and bundling leads to a lot of complications in transistors. You'd like to keep them close, but not too close. And so it's actually easier to get them all very close to one another because they're all touching at that point. But to get them just slightly is the bigger challenge. So that's where a lot of the frontier work is happening now.
Awesome. Okay, well, another frontier that we've talked about before is carbon nanotubes in quantum computing and quantum communication. So can you talk to us exactly how carbon nanotubes are used and maybe just like a brief overview of what quantum computing means?
Yeah, so quantum computing, it's good to discuss in relationship to digital computing. So that's your conventional computer. And in your computer, the information is represented as a 0 or a 1, or sort of an up and down. In a quantum computer, what you're going to have is a blending of the 0 and 1. And that requires you to have a different base computing element than you would have in a digital computer. Another thing that you would need in quantum communication is a means of encoding that quantum state with some element, and that element is often a photon, a single particle of light. And to realize quantum communication, you need to be able to generate single photons. And it turns out that carbon nanotubes are among the best options for making single photon emitters. So that's a frontier problem that we're working on in my lab. It turns out to get the single photons out, you actually need to intentionally disrupt the bonding of the carbon nanotube. We talked a little bit before about functionalizing the nanotube, and I said in a biological context, I don't want to covalently disrupt the nanotube network. But for single photon emission, that's exactly what you want to do. You want to have one of the bonds in the carbon nanotube disrupted. And what that will do is create one point on the nanotube surface where you can get the photons to be emitted, one photon at a time. So the functionalization of nanotubes is critical to getting this quantum communication application to work.
So how do you just disrupt like one bond?
Yeah, so this is done via a chemical strategy. And basically we have to come up with reaction conditions at sufficiently low concentrations that you're going to get one or at least a small number of these binding sites per nanotube. And so it's basically controlled by the chemistry that you're using to do the functionalization.
And I guess when we talk about quantum computing, one of the biggest things is because of the uncertainty of whether it's 0 or 1, so much more information can be passed. So when we talk about a comparison to today's digital computing, we know that it's better at silicon at lower resolutions, but can it be used in higher resolution, so above the nanometer scale, for quantum computing and still beat it? Because at that point, is it easier to produce than trying to get everything aligned at a nanometer scale?
Well, yeah, I mean, I think what you're driving at is that the number of bits you need in a quantum computer is much lower than the number of bits you need in a digital computer. And that's because each bit is no longer just a 0 and a 1, but it's a sort of a gradation of the two. And so that's absolutely right. In a quantum computer, for some algorithms, if you get to 100 or maybe 1,000 bits, you're already outperforming the digital computer where you would have billions of transistors. And so, yeah, that's sort of the promise of quantum computing. The challenge is that you need all of those bits to be working together, and the integration of the bits is a non-trivial endeavor. But that's where a lot of work is happening nowadays.
How far do you think we are from the use of carbon nanotubes being like integral in creating these quantum computing like systems?
Yeah, my guess is that they'll likely be used for the quantum communication, the single photon emitters. That's probably where they're best suited. And then likely
Gotcha.
other materials will be used for the quantum computing elements, the so-called quantum bits in your quantum computer. And that will likely be materials like superconductors, which are used in the Google quantum computer today. But ultimately, you're going to have to network them together, and the communication between them is going to be similarly important, if not more important. I mean, if we just had isolated computers and no internet, it would be a very different world than we have today.
Absolutely.
Do you think in our lifetime that I'll be able to have a quantum computer at home, or do you think that's a long shot? It'll most likely be concentrated in big areas where research is done.
Yeah, I mean, to be honest with you, I think the trend, and this is even the trend in digital computing, is that the computing will be done on the cloud, and the device you carry around will just be a sort of a way of connecting to the cloud. It's sort of not a great idea to put all of the computing in your cell phone, for example. You have enough to communicate with the cloud, but the cloud is doing the hard computation. So you'd send your job out to the cloud. The computation would occur in some server farm remotely, and then the output would be sent back to you. I think that would be the modality for quantum computing as well. In which case, you don't necessarily need to have a portable quantum computer, but you do need to have quantum communication from your device to that remote quantum computer. And that's why I think the quantum communication will be necessary to fully exploit quantum computing. And therefore, maybe in your lifetime, you won't have a quantum computer at home, but you'll still be using quantum computing located in some server farm that Google or Amazon or someone else is running for you.
Amazing.
Yeah.
All right.
Oh, I was just gonna say that quantum computing is so interesting and fascinating to me, but I still don't really get it. It's a very I understand the basics, but how that we are actually going to apply it in any meaningful way, I can't wait to see, because I just don't understand it fully yet.
Yeah, I mean it's very challenging to explain until you've learned quantum mechanics in some detail. And quantum mechanics is a subject that's taught typically late undergrad, if not grad school, to physicists. And the underlying conceptual framework of quantum mechanics is very counterintuitive if you live in a world of classical physics. The good news is, as I suggested, is this quantum computing technology, I think is likely going to be based in remote server farms where the user, it'll be completely invisible to them, and the details will not be important. All that the user will realize is that the algorithm is executed much more quickly than it was in the past.
It's clear that this area has a lot of potential moving forward. So I was just wondering, what advice would you have for MSc students who want to get involved with these CNT related research, or maybe even pursue a career in a similar field?
Yeah, so I mean, I think material science is a very good degree if you want to work on this topic. I mean, the control of the carbon nanotube structure is the name of the game. If you can figure out a way to synthesize it in a more scalable, a cheaper way, a higher purity way, all of these things have immediate downstream benefits for employing these materials in a wider range of applications. I think that's a very good discipline to work on if you want to work in this field. But it's one which is highly interdisciplinary. As I mentioned before, we had to know something about biochemistry to get the separation to work. The downstream applications require some knowledge of electronics or solar cells or batteries. And as a result, I would also encourage students who are interested in this field to take a broad perspective in their training, to take advantage of any opportunity to take courses in other disciplines, and to see those interesting connections between the disciplines. The students who have a combination of depth, maybe in material science, but breadth to see the connections across fields are the ones that are most likely to be successful.
I love that. And I feel like that research that you mentioned, where it's the carbon nanotube scale is connected to like the scale of like DNA, that wouldn't have happened if there wasn't that interdisciplinary study right there. So yeah, that's very good advice, and one that I'll definitely be taking into account moving forward. But thank you again, Mark, for coming on to the show today. We really appreciate having you on here, and we learned a lot.
Yeah, my pleasure. And I want to thank you and the audience for tuning in. And I look forward to many more carbon nanotube students and engineers in the future. So thank you, everyone.
Absolutely. Thank you for tuning in to this episode of the It's a Material World podcast. If you enjoyed the show, consider subscribing and hitting the like button down below. And if you'd like to support us on this journey, or simply show off your love for MSc, we actually released merchandise. And if you'd like to check out more of the designs, visit itsamaterialworldpodcast.com/shop, or use the link in the description. We'll see you soon. And in the meantime, go change the world.